Hey everybody, today we are going to learn about the nomenclature behind salts. Remember, these compounds, unlike covalent compounds, have a metal and a non-metal combined together. NaCl is a great example of this. So salts are a crystal lattice of repeating formula units like NaCl. A formula unit is just a repeating unit that repeats over and over again in the crystal structure, such as NaCl, which repeats over and over again over here, just about anywhere you look in the structure. The crystal lattice is one of the main reasons why salts are not covalent molecules or compounds. Ionic compounds are also electrically neutral. So, unlike covalent compounds, when we name salts, we don't ever use prefixes. For example, this is sodium chloride, and we don't say sodium monochloride, we just say sodium chloride, because we don't use prefixes. And something like Ki will be potassium iodide. Easy, right? Well, yes, for the most part, but we have to get to some special cations and anions that you will see very soon. So, when I mean very soon, I mean right now. Let's focus on cation naming. Metal cations that have one charge, like Na over here, or Ca right here, are just named after their element. For example, sodium in its cation form, which is Na+, will just be called the sodium cation, and this calcium 2+, would just be called the calcium cation in its English form. So anything with one charge will just be named after the element's name. Now we get to metals that can have multiple charges, meaning that, for example, chromium right here can exist as chromium 2+ or chromium 3+. So metal cations that can be in multiple charges are named a bit differently. So, for example, if I said that chromium 2+ was just the chromium cation, wouldn't that be vague? Because you couldn't tell whether it was the +2 form or the +3 form. That's why for cations, instead of calling this chromium cation, we will instead call it the chromium 2 cation. And we added the 2, which is written in Roman numerals, in order to specify that the chromium cation we're talking about is in its +2 state. So when you add a Roman numeral to the front of an element, that specifies the charge of the cation, and it's called the stock system. So, for the stock system, you basically have to know your Roman numerals. So, I'm going to use a new page, and we're going to go over the Roman numeral. So, I is 1, double I is 2, triple I is 3. Now, let me connect the top and the bottom so that it looks right. Now, IV is 4. V is 5, VI is 6, VII is 7, VIII is 8. And you won't go any further than this in chemistry for the most part. So you could either learn how to use the Roman numeral system, or you could just memorize this. I mean, either way works, honestly. So if you notice on the chart, most of these cations that have multiple charges are usually the transition metals, which go from 3 to 12. And there are 2 exceptions to this, and you should memorize this. So they are in green. So silver is always in a +1 form. So when you say the silver cation, that's fine, because silver can only exist in one form. So you don't have to say silver 1 cation. You could just call it silver cation. And same goes for zinc. Zinc will always be +2. So you can call this the zinc cation instead of calling it the zinc 2 cation, as I did with chromium 2 cation, for example. So let's talk about the charges of the ions that you absolutely have to memorize. Everything in group 1, which is shown here, will always be +1. Everything in group 2 will be +2, so like calcium 2 plus. And scandium in group 3 is +3. And you have to know that things in group 13 are also +3 as shown here. Now, don't worry about 14 as much, but let's go on to group 15. Group 15 will have 3 minus charges. Group 16, it's covered, but it's here, will have -2 charges, and group 17 will have -1 charges. And these elements here, the noble gases, will not form ions, so thus they don't have a charge, so we don't include it in our list of cations and anions. So to name anions, it's a little bit different, but since that's our next topic, we'll talk about it very soon. But let's talk about a few more exceptions that you should know. So this is mercury, and it comes in 2 different forms in its cation form. You could have Hg2 2+ or Hg2+. Now, Hg2 2+ is called mercury 1. And meanwhile, mercury 2+ is just called mercury. Wait, let me just erase that because I think I'm covering some numbers. I'm going to write it maybe right down here. Mercury 2+ is mercury with a parenthesis 2. So why is it this? Well, think about it this way. Hg2 2+ has 2 mercuries, and the 2 mercuries are sharing a 2+ charge. So each of them will have a +1 charge, which is why Hg2 2+ is called mercury 1. Meanwhile, mercury 2+ is just 1 mercury with a +2 charge, so that's why it's called mercury 2. And that's basically all the exceptions. And for these cations over here, these transition metal cations that have multiple charges, it's really your choice whether you want to memorize them or not. But the more you memorize, the larger the advantage you'll have, of course. And note that tin and lead, as shown here, have either +2 or a +4 charge. So I'd say that your job is to go over this table, look at all the elements and the different charges that they can have, and pick the ones that you might have to memorize for a class, or maybe do it for fun, or do it for the sake of learning. I don't know, it's really your choice. But take a look at this table. It's pretty useful, I think. So now let's talk about something called the traditional system. So I'm going to use a new chart or a new paper. So the traditional system of naming cations is a little bit outdated, which is why it's called traditional. The system that we use is the stock system. So let's take a look at 2 ions of the same element. Let's take gold. Gold can exist in a +1 or +3 state. So let's write that in our paper. So we could write this as Au+ or Au3+. So how would we name these using the stock system? Well, this would be gold 1. This would be gold 3. And that's the stock system. That's the one you'll usually use. Now there's this outdated system that might show up on bottles of gold if you ever have bottles of gold ions. So Au+ will be called, that's not right, will be called Oris, and Au3+ will be called Auric. So you might notice that Au and Au match the Au prefix, and this is because in the traditional system we use the Latin names for the elements. So in the last video, I believe that AU in Latin stood for aurum, so A-U-R-U-M. So what this traditional system basically does is they keep this first part, and this second part, they basically change it to an is or an ic. Now, how can you tell if it's an is or ic? Well, the is usually refers to the lower charge, and the ic stands for the larger charge. So let me show you another example. Let's take lead. So on our little chart we drew here, lead is Pb right here, and lead is shown to have a +2 and a +4 charge. So if we go back, wait, let me erase this first, because this is supposed to be +3, but now it looks like a +2, and that's not good. So this is a 3. Sorry for the confusion. Now let's go back here. So let's take a look at lead. So lead can be written as Pb2+ or Pb4+. This would be called lead 2, and this would be called lead 4. Now in the traditional system, we call this plume bis, and the is because it's the lower charge, and we have plume bic. I don't even know if I'm pronouncing this right. I hope I am. But the ic is the larger of the two. So we use the is and ic usually when the ion only exists in two forms, such as lead, which exists in +2 and +4. But we don't usually use this system, so I would just say don't worry about it that much, but be aware that exists. So now let's talk about naming anions. Do you remember in the last video how I told you to add the ITE ending to the second element, like Cl will become chloride? Well, guess what? The rule will be useful in naming salts because the anion in the salt will basically have the "ide" ending of the element, just like how we named the second element in a covalent compound with the "ide" ending. So for example, CO2 was carbon dioxide with the oxide instead of oxygen, and the same rule applies for salts. When you have NaCl, the Cl is not called chlorine, it's called chloride. And remember, for salts we don't add the prefix, which is why we didn't have to say monochloride. So Cl minus, oops, sorry, I forgot to put the minus, but Cl minus is chloride, O2 minus is oxide. And note that if you simply have something like Cl, which is the atom and not an ion, this is just called the element of the name, chlorine. You only add the ide form when it's an ion, such as here. Now we need to talk about one more thing. In the last video, I introduced to you what a polyatomic ion is, which is basically a compound or a molecule that has a charge. So this is a list that I compiled of the different polyatomic ions that are most relevant and most important, and you basically either memorize the ones you need to, or you memorize them for fun. So now let's look at a few tricks that are done with polyatomic ions. Let's take a look at PO4 3-. Now where is that in the chart? It looks like it's over here. That's called phosphate. If we add an H to make it HPO4 2-, it is called hydrogen phosphate. So if we add another H yet again, then we call it dihydrogen phosphate. So notice how each time I add an H, the negative charge becomes smaller by 1. So it goes from -3 to -2 to -1 every time I add an H. So think of an H as like, a +1. That's canceling out the -3. So in this case, we have two H's, so it would be +2, and that would be -3, and the overall charge would just be -1. I know that's kind of a confusing chart, but I'm sure you got it. And yeah, that's one trick in the chart. Now, there is also another trick, HCO3. So let's find where HCO3 is. Hydrogen carbonate. Hydrogen carbonate is also called bicarbonate. That's something you should know. And instead of calling it hydrogen carbonate, you could call it bicarbonate if you'd like. They both work. So let's look at trick number 2. Let's take chlorate. Where is chlorate? Over here. If you add a per to the front, you get perchlorate, which is over here. And notice when I add the per, I add 1 oxygen atom to it. So it went from 3 oxygen atoms to 4 oxygen atoms when I added the per to it. And note how the charge still stays the same. Now, what happens when I change the 8 in chlorate to an ite, like chlorite? Well, if I change the 8 to an ite, let me erase that, I will remove an oxygen, so ClO3 minus will become ClO2 minus, so minus 1 oxygen, but the charges still stay the same. Now, what happens if I add a hypo to the chlorite? Well, if I add a hypo to the ite form, then I get rid of another oxygen yet again. So hypochlorite is right here. So notice how that has 1 oxygen and has minus 1 charge. So it got from 2 to 1, but the charge still stays the same. So chlorate is not the only thing that could do this. Iodate and bromate also do this trick, but the only difference is that instead of a Cl, you have a Br or an I. So keep a note of that. And we can apply this rule to something different too. Let's take sulfate, for example. Sulfate is SO42 minus. Now what happens if I change the 8 to an ite? Well, that just removes 1 oxygen. So that's what you see. 4 goes to 3, and the charge still stays the same when you go from sulfate to sulfite. Now let's look at phosphate. Phosphate is, where is this? Phosphate is right here. PO43 minus. Now what if we change an 8 to an ite? Well, it gets removed 1 oxygen. So phosphate to phosphite, same charge, minus 1 oxygen. Now what if I did hypophosphite? Now this is just one word, but I kind of split it into 2 lines. So if we add a hypo to the ite form, then we're removing 1 oxygen. So phosphite is PO3 minus, so hypophosphite would be, well, PO2 3 minus. And remember, we keep the charge the same, but we just remove 1 oxygen. So let's now talk about the hierarchy of these prefixes. So the hierarchy starts at the 8 form, of course. So 8 will be the ending, and you had something in front. And if you want to add 1 oxygen, then you would have to add per blank 8. And if you want to remove 1 oxygen, well, you would change an 8 to an ite, so it would be blank ite. And if you want to remove yet another oxygen, then you call it hypo blank ite. So you add the hypo. So this is a hierarchy, and the charge stays the same. So now let's go back to one last special rule. So let's look at the transformation of cyanide to thiocyanate. Well, cyanide is Cn minus, and notice how thiocyanate is just an S added to the front. So that's how thio works in that case. Now what about thiosulfate? Well, that comes from sulfate, which is, I don't know, looks like it's over here. So when you add the thione from sulfate, you are changing one of the O's to an S. So we had 4 O's at first, but if we change one of those O's to an S, then we have an extra S and 1 less O. So thus we have S2O32 minus. Notice how we didn't make the switch in cyanide to thiocyanate because cyanide didn't have an O to begin with. So we didn't have to make the switch. But in thiosulfate, we had to make the switch in sulfate by changing 1 O to an S. So that's how the thiols work. So the only thing left that we have to do is how to combine the cation and the ion together. So you want to make sure that the charges on the cations and anions cancel out, so when they combine, they're electrically neutral. And the cation comes first, and then the anion comes next. So basically, all cations are metals, and all anions are nonmetals. So let's take an example. Let's take Na plus and Cl minus. Oops, let's do a different color. Cl minus. So this would combine to be Na and Cl. And notice how the charges cancel out, because positive 1 minus 1 is 0. So how would we name this salt? Well, NaCl would be sodium. Remember, no adding prefixes. It would be sodium and then chloride, because we use the "ide" ending instead. Now, let's look at something more complicated. What about if I said that the cation was Na plus, oops, I'm messing up the colors. Let me go back and change the colors. Na plus, and for our anion, let's make it O2 minus. So we want to balance out the charges, so what if I said we have 2 Na pluses and 1 O2 minus, so that overall positive 2 minus 2 is equal to 0. So let's write that out. Na2O. So remember, when you write the salt, you don't add any charges because overall it's neutral. So what would this be called? Well, sodium, remember, sodium has only one charge, since on the table we said that group 1 has only one charge, and thus you don't need to use the stock system, which uses Roman numerals. We only use the stock system when we're dealing with things with multiple charges, such as those in the transition metal spot, which we'll look at later. So this would be called sodium oxide. And remember, it's O2 minus because it's part of the trends in the periodic table that we had to memorize. So let's look at our next number. What if we wanted to combine something like Pb 2 plus and something like N3 minus? So we would need 3 leads and 2 nitrogens so that their charges cancel out. And notice a fun trick is that these two match and these two match. So that's a fun trick if you're ever stuck with wondering how many of each you should have. So this would be plus 6 and this would be minus 6, which is 0, which is great. So let's do that. So Pb3 and N2. Now, how do we name this? Well, there are several ways to name this, so let me erase. So remember, since lead has a plus 2 and a plus 4 form, we had to use the stock system. So this would be called lead 2 nitride. And this is nitride because it's not a polyatomic ion, it's just an element with a charge. And remember, we just have to use the "ide" form of it whenever we're dealing with one element. So this is lead 2 nitride, or we could call it plume bis nitride if we want to use the traditional form, but we usually stick to this form. So let's look at another example. What if we combined iron and phosphate? So my challenge is for you to determine the charge on iron. And I'm not giving you any information except for the fact that they combine in a 1-to-1 ratio. So we know that phosphate, according to our list of polyatomic ions, has a minus 3 charge. So let's use that to our advantage. So if this has a minus 3 charge and they're in a 1-to-1 ratio, that means that iron must have a plus 3 charge, and they have to cancel out to be 0. So this iron is in its plus 3 form. So let's write out the name now. So this would be iron 3 phosphate. Or, using the traditional system, we could call it ferric phosphate, because iron exists in 2 plus and 3 plus, and since 3 plus is the greater of the two, we use the ic suffix. And notice how I didn't change this ending into an "ide" form, because we only do that when we have one element, like N, or O, or F, or anything. So let's do one more example. What if we combined two polyatomic ions at once? So NH4 plus and NO3 minus. Well, we know that this is a 1-to-1 ratio because plus and minus is 0. So our salt would just be NH4 NO3. And this is called, in English, ammonium nitrate. And we don't use the stock system since ammonium has only one charge, and it's also a polyatomic ion. So you might look at this and you're like, oh, that looks like a covalent compound since it has no metals. But don't be fooled. NH4 is an polyatomic ion, and NO3 is also a polyatomic ion. So whenever you see NH4 in a salt or in any compound, you should most likely think that it's a salt and not a covalent compound. So just be wary of that. So let's look at one more. What if I said that there is a salt called silver perchlorate, and I wanted you to write the formula unit for it, since in salts we use the word formula unit instead of, a compound or a molecule. So what would be its formula unit? Well, we know that silver is Ag+, and we know that perchlorate is just chlorate, but with an extra oxygen, so it would be ClO4-. So let's combine this. If this is +1 and this is -1, then, they're 1-to-1 ratio, since +1 -1 becomes 0 when you add them up. So when you combine them, they would just be AgClO4. And notice how there wasn't a charge here, even though silver is a transition metal. And that's because silver is one of those transition metals that only exist as one charge. So remember, in green, silver is a +1 charge, and zinc is another one of them. It only exists in a +2 charge. So let's go back here. And I think we've done enough practice for today. So I hope you learned a lot, and thank you for watching.